And
Julien, I'm going to introduce you while you
yeah,
get your
exactly.
slides up. So Mike introduced you earlier, but just a reminder, Julien is an associate professor and director of the Neuroimaging Research Laboratory in the Department of Electrical Engineering at École Polytechnique de Montréal, and he's also an associate member of MILA, which is the Quebec Artificial Intelligence Institute, and he is the Canada Research Chair in Quantitative Magnetic Resonance Imaging. He's going to tell us about CODA, this an open source platform for privacy preserving analysis of distributed biomedical data.
Thank you for the introduction. So federated learning has gained important momentum for applications in medical imaging, as we all know, and we've heard about the FETS study presented by two previous speakers, Alexandros and Sartak, which show the proof of concept application of FL for the segmentation of glioblastoma in brain MRI scans. So it's a very large scale study involving 71 healthcare institutions, maybe more today, across all continents. So as you can imagine, this is an inter-institutional study requiring massive efforts in terms of logistics, knowledge dissemination, standardization of data preprocessing, communication between sites, and so on. So, kudos to the team to organize all that study. But there's one important aspect to note is that, most recent FL studies in the medical field, models are usually trained locally using dedicated servers after manually extracting and creating the data from the medical picture archiving communication system, also called PACS, because that would have added a significant layer of complexity to the study if the data would be, or if the nodes would be directly connected to the PACS system. So while the proof of concept was brilliant and useful to demonstrate the usefulness of federated learning for medical image analysis, this type of approach is not fully integrated into the clinical infrastructure, and it requires having a local ITs, data scientists, pooling and curating data, which is not a sustainable solution for a fully integrated and automated FL ecosystem. So what is missing to achieve a real continual federated learning infrastructure that is embedded into the hospital's workflow includes an infrastructure that is directly connected with the hospital's PACS, where communication protocols for the FL infrastructure is compatible with institutions' IT policy. So speaking of the Quebec hospitals, the NVIDIA Flare OpenMinds are not compatible, like use protocols that are not compatible with the local hospitals. Standardized clinical and imaging protocols and metadata, and also training and inference APIs that are easily deployable to all sites. And also an end-to-end solution that is compatible with the local jurisdiction and that is accepted by the local IRBs for all the participating hospitals. So the unmet needs that I just mentioned motivated the development of the CODA platform. So CODA stands for a collaborative effort between hospitals in Quebec and Ontario to build a standardized database of demographic, biological signals and images that can directly be accessed from the hospital's PACS. So each site can train models and exchange model parameters using secured communication protocols between other sites. The name CODA originates from Analyse collaborative des données pour améliorer les soins cliniques chez les patients. The project started with COVID-19 as a proof of concept, but has since been expanded to other applications. So it currently includes 8 hospitals in Quebec, 1 in Ontario, and there are current plans to expand it to other provinces and outside of Canada. The people who worked on developing the CODA platform are listed here. There's notably Pascal Saint-Onge, project manager, and the executive committee include Michael Chassé and Louis Mully. And my team is involved into adding the MRI features. So I will very briefly describe the building blocks of the CODA platform, which is done in collaboration with the Valeria Institute in Laval. in Quebec City, sorry, Université Laval. The overall architecture is fairly complex. So the overview is like that. So this block here pertains to a specific site, let's say a hospital. So it contains 3 virtual machines or VMs. The first VM is called the red VM, is the transit zone and contains the patient identifiers. So this VM is connected to the hospital's PACS directly. That's why it's called red. It's highly secured. And the patient data are converted to the FHIR format, FHIR, which is a JSON file designated for medical applications with standard fields such as sex, age, and so on. So this VM is only accessible to some personnel inside the hospital. The second VM, called the orange VM, is responsible for sending the de-identified data to a MineIO storage platform. So in brief, MineIO is a high-performance object storage released under the GPL license, and its API is compatible with Amazon S3 cloud storage service. So each object data is assigned a URL that redirects to a physical file. And then the 8-box manages a PostgreSQL database of these URLs. And finally, the third VM, called the green VM, is responsible for launching specific tasks via APIs that are written by researchers. For example, statistical modeling to describe the data, meta-analysis, or deep learning to prepare data, train, and test a model. And the output of the task is sent to the hub institution. So what's the hub institution? It's a physical location that runs APIs that controls the flow of requests from the green VM. So in the case of the COVID-19 project, the hub is hosted by Valeria at Université Laval in Quebec City. And the hub API is responsible for aggregating the request from all the sites and computing the global model. And to monitor all this, there is a dashboard that is accessible from a browser. And it can notably show the data, perform personalized requests, run meta-analysis, perform descriptive statistics, visualization of results, interface of model training, and monitor the connectivity. And all the modules of the CODA platform are open source and accessible via GitHub. So the CODA team is still working on some aspects, and notably with the institutions and government, to set up template ethics documents, such as consent form, data sharing agreements that are compatible with the local IRBs, so that every researcher could use clinical data for their research. The current limitation of the CODA platform is that it can only support tabular data under the FHIR format. FHIR does not support images, which are typically stored in DICOM format. So we are now working notably with the team of Philippe Després at Université Laval to have CODA platform support medical images. And in brief, what we have in mind is that images will be de-identified in the red zone and sent to the orange zone. And there, a couple of technologies will be, which will be used, including ORTANK, which is a DICOM server to store images, the KOPS platform to view these images, 3D slicer to create ground truth labels, and those labels will be used for model training and testing. And finally, once the images are accessible via the CODA infrastructure, we need image-specific learning APIs. And so there have been recent developments in this direction. So I invite you to look at also this website that is from the group of Philippe Després. a little shout out on our developments from the lab is the API for model training will be leveraged by an open source platform called Evadomed, which is an integrated framework for medical image analysis with deep learning based on PyTorch. Some of the features include the possibility to dump any imaging data set that follow the brain imaging data structure called BIDS, which was mentioned before. Evadomed includes some, bleeding edge architectures and also a few tutorials to make it easier to dive into this ecosystem. And in parallel, we are also working on finding the best strategies to combine data sets from multiple centers, notably to account for catastrophic forgetting or model shift. That's something that was mentioned in one of the previous talks. And this is the work of Naga Kartik, a PhD student in the lab. Paper was presented at the NeurIPS workshop last year, and it compares different approaches for training an MS lesion segmentation model across different sites. So namely, Naga compared a model trained per site, so a single domain, with fine-tuning, with experience replay, and also the last one is aggregating all the data set together, which is also called multi-domain training. And results suggest that experience replay, where we use a buffer of a couple of data from the previous site, suggest that the experience replay have the higher performance when compared to aggregating all the data set together, which is done with a multi-domain training. So the next step for this will be to apply this in a real-world federated learning scenario. So with that, I'd like to thank all members of the lab, the CODA research group, funding sources, and thank you for your attention.
All right, thank you, Julien. Let's see, we do have a question from Ashley Pike. Are image processing methods developed in research-based scanners showing robust effect sizes able to replicate similar results from clinical scanners obtained imaging? A dilemma exists in translational research in MS, in the US at least. Robust effects in research methodologies, datasets cannot be directly implemented in the clinical setting for multiple reasons, such as difference in scanners, insurance covering these new modalities.
Yeah, that's a great question. It was a bit discussed previously, and it's still an unsolved problem. It is true that there's large variability of image quality across sites. I think that one way to there are different approaches to this question. One approach which I've been undertaking for the past couple of years is to work on the standardization of imaging protocols. And I'm particularly interested in the spinal cord. So we've put together basically a standardized protocol for spinal cord imaging across different vendors, Siemens, Philips, GE, now Canon. And the goal of this is precisely to mitigate the issues raised by this question, and to make sure that the data look a bit more closely together, look more similar, so that the image processing that is applied would work better. But we are far from getting there. Standardization also means that there is less room for innovation. If an example is the MP2 range sequence that has recently been introduced. Some groups show that it's useful for seeing MS lesions. It's not necessarily yet integrated into modern processing pipelines. So there is a fine balance between standardization of imaging protocols, but also leaving room for innovation. Another aspect of the question is making sure that the models or the processing generalize as much as possible to the existing data set. I think this is one of the motivation of doing federated learning, is that we want to train and test models across the largest possible variety of images and sites. So hopefully that approach will help. Yeah.
Right. Are there other questions? So Julien, you mentioned that the imaging component of CODA is sort of still a work in progress. But yeah, so are there so in terms of the projects that you're targeting in terms of initial projects, is MS one of those projects that you're targeting?
Yeah, exactly. So yes, it is still integrating the imaging part is still a work in progress. I've heard a couple of days ago that there have been significant advances on the topic. So well, I have my team has to look into that. We need to get together, but the bottom line is that we are getting there, and my particular motivation with integrating the imaging aspect is MS lesion segmentation. That would be the next proof of concept that I'd like to try across the different hospitals in Quebec as a starting point, and maybe expanding that beyond.
All right. Are there any other questions?
One for Michael, yeah.
Yep, Mike.
Yeah, thanks, Julien. I mean, that's really tremendous. I'm particularly interested in the work you mentioned from your student with the multi-center training because it's clearly so relevant. I mean, that's a really interesting point. I'm not sure I fully understood all the details, but so I mean, can you talk a little bit more about maybe some of the ways that we would how we would synthesize models together? Because it sounds like he was saying it's not necessarily best to just put all the data together in one giant pile, but maybe have some sort of separately trained things or fine tuning for different sites. Is that something we can still do in a federated way, or how does it work together? Sorry if it's a naive question.
No, that's a great question, and yeah, I think that's something that is part of the research that can be spin-off from those. After we put together the infrastructure, there's a lot of research that can be done and how to properly done federated learning research and aggregating different data sets. And as you said, the point of this article from Naga was to say that by using a subset of data from another site and fine-tuning the model, it provides better performance than just pulling all the data together and training a single super model. Let's say, if Naga is on the call, he could also add a few words to it. Sorry to put you on this, Naga, if you're here.
Yes,
yeah.
Yes, I am. Yeah. So yeah, I guess that's precisely what the initial experiment was. I mean, it has been shown in the continual learning literature that sometimes putting random samples in your memory buffer works well, and it's also a hard baseline to beat. But one of the things that I wanted to try for the next phase of experiments was to be more specific on how and what samples to be stored in the memory buffer. So if you can find a metric or based on uncertainty or any other form of quantitative measures to sample some images into your memory buffer, then that would be better than training your model entirely on the entire data set and comparing the performance. So that's one of the ideas that I had about this.
Thank you.
And I see that Tal Arbel is also in this meeting, and her lab has done a lot of amazing work also addressing this particular question on how to aggregate multiple data sets and how to improve models. Sorry to put you on the spot, Tal. You're muted. Hold on.
Thank you. Yes, this is an important issue that we're also looking at. Very impressive talk, Julien, and I'm interested in more discussions later on this. So we can join maybe forces. Awesome. But Brennan, who is a research scientist at Mila, is working in our lab, will present some of our recent work later at 1. Thank you.
All right. If there are no other questions, I'm going to go ahead and have us adjourn until 1 p.m. so that